Welcome back. So I already talked about the playout agent in TimeFlex, and next I want to talk about its boosting component. The booster, it's basically an optional component, so you don't need it, for instance, if you are using TimeFlex in combination with Suit, because in Suit, like I explained earlier, we have actually extended its call graph analysis framework Spark to be able to directly read in the logging files that TimeFlex generates. So Spark has a specialized or uses a specialized parser that is actually reading in these files and then incorporates the results into the call graph that it builds. But the thing is, we also wanted to support other kinds of static analyzers. For instance, there's also Wala by IBM, and there's also the Duke framework by Yanis Marakakis and his colleagues. And there are other static analysis frameworks out there that all have, or at least used to have, the same problem, that they don't really know how to deal with reflective calls. Some of them have, worked on this problem as well. I'll still be talking about this, but some 10 years ago, there was basically no reflection support in any of these frameworks. So we wanted to give them a solution as well, but we didn't want to force them all to write their own, parser for this file format and adjust their call graph construction. And this is why we actually implemented this boosting approach. And the idea is that the booster, it takes your original reflective program, like you see one here, and it converts it into a statically analyzable version without reflection. Okay, so for instance here, we again have some variant of this program that I showed you earlier. So we are loading a given class. In this case, it's loaded based on some command line parameters. So we have no idea what this is going to. Here we even have a constructed string for the particular method name. So we might also not be able to interpret this very easily. And so the question is, where do these different calls actually go to, right? So which class is being loaded here and which method is actually being invoked here? And now we can actually use the playout agent and look at its log file, and we will see, for instance, that this is actually loading a class called evil at line 6. And then at line 8, we are calling the method doEvil on this particular class. Okay. And now that's what we get out of the playout agent. And now the booster will do the following. It will incorporate this information into the original program by rewriting it. And let's take a look what this looks like here. So we boost this. And now this is what you get. So everything that has nothing to do with reflection is untouched. In particular, we still have this statement here. We still have this statement here. And also, in fact, even this get method call here, it's not touched because we are only interested in this case in class for name and method invoke calls. But these two calls, like you see, they have changed. And in particular, let's first look at these underlined lines here, okay? So previously here, we had this class for name call, but we know for a fact that by looking at the logging file, the only class that is loaded here is the evil class, right? And so here we now use a class constant instead to actually assign this particular variable here, this particular class constant. And Suit and Spark and also pretty much any other call graph construction engine can recognize these class constants. So these analyzers will now understand that the variable CL can be assigned an object of type evil, right? Or evil, the class of evil, let's say, right? The same down here. So previously we had a method.invoke call here, but now we have actually inserted the actual target method call directly into the program. Okay. Now, you may wonder, why is this all guarded by this additional weird code that you see here, right? And you see the code is somewhat similar, but it's not identical. Well, this has to do with the fact that we may still need to run this code in the end. So in particular, um, you may want to take the boosted code that you see here, and you may want to run it in order to see whether you have actually covered all the different cases, for the different inputs that matter to you. And through these guards that we insert here, when you now run this code, if you happen to run it in the same configuration that was already in the logging file, so using the class evil here as a parameter, and then using do evil here as the string that is being constructed here, then it's all fine. And these methods, or in particular this method, will be invoked, and this class will be instantiated. But in case you deviate from this previously recorded run, then you will hit one of these else branches here, and then we will actually warn you about it. So we will warn you about the fact that you're now executing functionality that was not previously recorded. And then we will actually fall back to the method call that was originally in the program. So we will again call class for name with this argument that we don't know anything about, or we will call method.invoke down here. Okay. So this was just necessary as part of our experiments, but it can also be an important feature in real life if you want to make sure you get the right kind of coverage. And in fact, these branches, they are also not hurting the static analyzers because, like I told you earlier, basically all the call graph construction engines, they are flow insensitive, and therefore they don't take into account these different branch conditions here anyways. The only thing that matters is that somewhere in the program there is a statement that assigns this particular type to this variable. Then this will become part of the points2 set of CL, no matter what. And therefore, then here we also know that, likewise, we here also know that this particular method call can be invoked, right? So that's sufficient. Yeah, and I just explained that to you already. So the booster itself, it's also implemented on top of suit. So if you want to boost code, you basically give a jar file as an input, or you give some program as an input to suit. You would then also give it a logging file as an input that was recorded by the playout agent, right? And so basically everything that's output by the playout agent, you can just provide to suit. You can just give it a pointer to this out directory. And then suit will instrument the program, or will transform the program directly on the Jimple intermediate representation. So we will convert the program into Jimple. We will insert these additional statements like I just showed you. And then we will write this out to another directory or also into a jar file, depending on how you configure it. So basically, you then obtain a boosted version of the program. And the nice thing is now that this boosted version of the program, you can give to any static analysis engine, right? So you could give it to Dupe, you could give it to Wala, probably also to many other static analyzers. And for this boosted program, they will then give you a more complete call graph. It's still, its completeness still depends on the dynamic runs that you actually recorded during the playout that you did prior to the boosting. Depending on whether or not you recorded a comprehensive set of runs, the boosting might actually really help. And like I said, for Spark, if you want to use Spark, you don't really need to do this. You don't need to boost the program because you can just read in the Tamiflex log files directly. So just again to show you this on this diagram here, how the booster works. So basically here, the booster, it will give you, it will take these class files that have been written to disk by the playout agent, right? So this is dumping every loaded class to disk. Then we will boost this and we get these manipulated classes. And this is then given to these classes are then given to the static analysis. That can then do something without it. It might even itself manipulate the code if it wants to. That doesn't really matter. But let's just say, for the sake of an example, right, then maybe we're given this to Wala, and Wala also does some static analysis and some code instrumentation. So we get yet another different class here. And then there's another question. So if we have a setting in general where we have a static analyzer that is not just analyzing a program, but it's actually implementing a optimization of a program, let's say, or also an instrumentation of a program, then you have these modified class files, right? But the question is then, how do you get these class files back into the original code locations, right? So I just showed you earlier that there are applications that have a pretty obscure way of loading classes, right? So they load classes from, nested jar files, for instance. They load classes from the internet in the worst case. So definitely from non-standard locations. And if we now modify bytecode, we might not even have access to these locations, right? So we might still be able to repackage some jar files, but that may not even be fun, right? It might be rather tedious and error prone. But if code is loaded from the internet and we don't have access to that server, then what do you want to do, right? I mean, we couldn't possibly just hack the server for the sake of running some experiments to see whether our optimized code is running faster or so, right? That doesn't really any make sense. So the problem is really as follows. So assume we have statically analyzed a program using all the class files and the log files and put the log file in the out directory. And then we assume that our static analysis has further transformed. So for instance, optimized these classes and put the transformed classes into some transformed directory. Then the question is, how do we manage to package all these transformed classes back into their original locations, right? So in the case of Da Capo, we saw this. We might actually need to package these classes back into these original nested jar files that they had been extracted from. And so the packaging problem is that the playout agent dumped the classes no matter where they were loaded from, right? It dumped it all in the same directory. They could even have come from the web. And in general, there is no easy way to get these classes back or the transformed classes back to these locations. And therefore, we actually don't do this. We rather play a trick again. And I think it's really a nice trick. So we actually cause the program, when it is running, to instantly swap out at runtime every loaded class with the appropriate transformed class. So we let the program load the original class that it wanted to load, maybe even from the internet, but just at the time before the program is about to instantiate that class, we are actually intercepting the program and we are swapping out the definition of that class. We are swapping it out by the definition that we have in this transformed directory sitting on disk. And this is exactly the task of this play-in agent. And in the next video, I will explain to you how this works.